Hello everyone, we are from Group 47. We will explain about our game, The Little Squares. First, we will explain the rules of the game. Then, we will make a demonstration of the game. After that, we will take a closer look at our game and explain the theorem related to our game. And finally, we will show the strategy by implementing the theorem in our game.
We will now explain the rules of the game. First, draw a rectangle with n times m squares, with n and m are elements of positive integer. Then you can put any number of obstacles anywhere inside the rectangle. From here onward, obstacles will be represented by black squares. Second, two players take turns to play the game. In each player's turn, he or she colors the rectangle with 1 by 1 square or 2 by 2 square. You cannot color a square with an obstacle in it.
Next, the same square can only be cleared once. The player who cannot make a move loses. In this example, it is the blue player's turn and he cannot make any move since there are no empty square left. So the red player wins. Here is the example of how we play the game.
Now, we take a closer look at our game. First, this game is a variant of the game of name. We assume that you already know the strategy for the game of name. Then, there is no cycle in this game. Here's the proof. Let P of x is the number of empty squares in X. Then, for all y, if y is one of the possible next state from X, then P of y is equal to P of x minus 1 or P of y is equal to x minus 4, because you can only color a 1 by 1 square or 2 by 2 square. Then, P of y is strictly less than P of x. Let there be a possible move from x to z with a path of y1, y2 to yn, with y1 is equal to x and yn equal to z. Let qm be p of y1 bigger than p of ym, where m is bigger than 1 and less than or equal to n. q2 is true from what we have proven before. Let qk is true where 1 is less than k and less than n. Then qk plus 1 equal to p of y1 bigger than p of yk plus 1. P of y1 is bigger than p of yk from what we assume, and p of yk is bigger than p of yk plus 1 from what we have proven before. Therefore, p of y1 is bigger than p of yk and bigger than p of yk plus 1. Therefore, p of y1 is bigger than p of yk plus 1. Therefore, qk is true for n bigger than or equal to k, bigger than or equal to 2. Therefore, p of y1 bigger than p of yn. Therefore, px is bigger than p of z for any x and z such that there is a possible move from x to z. Let there be a possible move from a to b. Then, p of a is bigger than p of b from what we have proven before. Then, let there be a possible move from b to a so that there is a cycle which contains a and b. Because there is a move from B to A, then P of B is bigger than P of A. This is a contradiction. Therefore, there cannot be a possible move from B to A if there is a possible move from A to B. Therefore, there is no cycle in this game. QED. Then, there is a finite number of possible states. Here's the proof. We define def x as maximum number of moves from x to the end of the game. If x is the end of the game, def x is equal to 0, because it is already the end of the game. If not, def of x is the max of def of y plus 1, such that y is one of the possible next state from x. Then, let there exist a state z such that z is one of the possible next states from x and def x is less than or equal to def z. Def x plus 1 is less than or equal to def z plus 1. Then def z plus 1 is less than or equal to max of def y plus 1, such that y is one of the possible next states from x. Then it means def z plus 1 is less than or equal to def x. Def x plus 1 less than or equal to def x, which is a contradiction. Therefore, for all z, if z is one of the possible next state from x, then depth x is strictly greater than depth z. Because the depth of the current state is always less than the depth of the previous state, it means the depth of the state will get smaller by every turn. This means the depth of the current state will reach 0 eventually and the game will end. QED. Because there is no cycle in our game and there is a finite number of possible states, every game ends in finitely many moves. Then there exists an optimal play where both players play optimally. A player plays optimally if he or she always makes the best move in his or her turn. The best move is the move that makes the opponent in the worst situation possible. For example, it is the red player's turn right now. He can make 2 times 2 square at c5, or a 1 times 1 square at any of those empty squares. If he plays optimally, he will color a 2 times 2 square at c5, so the blue player will be in a lose situation. Otherwise, if the red player put a 1 by 1 square, he will lose, which is not the worst situation for the opponent, which is the opponent wins. In the subsequent example, we assume that both players play optimally. Because both players play optimally, there exists a winning state, which is a state which secures a winning for the current player. There also exists a losing state, which is a state in which there is no possible way for the current player to win. Finally, this game is a combinatorial game. A combinatorial game is a game in which there are two players. There is a finite set of positions available in the game. The rules specify which game positions each player can move to. Players alternate moving, and the game ends when a player cannot make a move. The game eventually ends. This game fulfills all the criteria for a combinatorial game.
Sprague-Grundy theorem. To derive a winning strategy for the game, we are going to use the Sprague-Grundy theorem. Why is it applicable? The condition for Sprague-Grundy theorem is that the game must be an impartial game, which is the case for this game. Impartial game is a game in which the set of allowable moves depends only on the state of the game. So, the only difference between player 1 and player 2 is that player 1 goes first.
Every possible position in the game is considered as a state. We define a winning state X as a state such that there exists Y, such that Y is the possible next state from X, and Y is a losing state. We define a losing state X as a state such that for all Y, if Y is the possible next state from X, then Y is the winning state. By definition, a state with no empty square left is a losing state. Every state of the game can be classified as either winning or losing state. Here's the proof. Let A be a set of states which are neither winning nor losing. Let X be an element of A such that for all Y element A, depth X is less than or equal to depth Y. Let Y be a possible next state of X. Then depth Y is less than depth X. If Y is an element of A, by definition of X, depth X is less than or equal to depth Y. This is a contradiction. Therefore, Y is not an element of A. Therefore, Y is either winning nor losing. If all Y is winning, then X is losing by definition of losing. If any of Y is losing, then X is winning by definition of winning. Then X is either winning or losing. QED.
This is an example of a winning state. By coloring any 2 times 2 square, the current player wins. Because after coloring the 2 times 2 square, both players can only color 1 times 1 square. So the moves will look like this. The current player will color 2 times 2 square here. Then the other player will color 1 times 1 square here. And the current player will then color the 1 times 1 square here. This is an example of the losing state. The current player can only color 1 times 1 square, then the next player will color the other square. So the current player loses because the current player cannot make a move anymore. How to calculate the number of a state? Number of a state is a number that represents the current state of the game. Number of terminal state is 0 by the definition. Number of non-terminal state is the minimum excluded value or max of the numbers of all the possible next state. Max itself is defined recursively. Max of S is equal to the minimum value of n greater than or equal to 0, where n is not equal to x for x is for all element x of S, where S is a set of natural numbers.
Now this is our current state. If we put 2 by 2 here, there will be no square left. And this is the next state. And if we put 1 by 1 here, this is our next state. There are another 3 states, but it is the same with this state because it is achievable by rotating this state. And if now this is our current state, and we put 1 by 1 here, then this is our next state. If we put 1 by 1 here, this is our next state. If we put 1 by 1 square here, or here, or here, or here, then we will get this state. Then there's only one option. We will have to put 1 by 1 here, and there will be no empty square left. Then by definition, if there is no more empty square, the number value is 0. Then the number value of this state is 1 because the minimum extruded value is 1. The same for this. The minimum extruded values of this state is 0 because based on the next state is 1. The same for this too. Now for this, the next state is 0 and 0, the number. Then the minimum extruded value is 1. For this, there is no empty square left. The number value is 0. And for this, we have 1. Then the minimum extruded value of this is 2. So the number value of this state is 2.
Why it works? A state is a losing state if and only if it has the name value of 0, and a state is a winning state if and only if it has the name value of not 0. Here is the proof. Let P of k is equal to the for all x, if the depth of x is less than or equal to k, then nim of x is equal to 0 if and only if x is losing for any k in natural number. Then P of 0, because if depth of x is 0, it has the nim value of 0 by definition and it is a losing state. For any n in natural number such that P of n, for any state x, if depth x is less than or equal to n, then nim x is equal to 0 if and only if x is losing. Then for any state of x, if depth of x is less than or equal to n plus 1, x is either losing or x is winning. If x is losing, for any state y, if y is the possible next state of x, y is winning by definition of a losing state. Depth of y is less than or equal to n. Nim of y is equal to 0 if and only if y is losing. Therefore, nim of y is not equal to 0. Therefore, nim of x is equal to 0. Therefore, x is losing. If x is winning for some state y, y is the possible next state from x. Y is losing by definition of a winning state. Let A be a state such that A is the possible next state from x and A is losing. Depth of A is less than or equal to n. Nim of A is equal to 0 if and only if A is losing. Therefore, nim of A is equal to 0. Therefore, nim of X is not equal to 0. If nim of X is not equal to 0, then X is winning. Therefore, X is losing if and only if nim X is equal to 0. Therefore, Pn plus 1. Therefore, by induction, Pn for any n in natural number, QED. This definition of winning and losing state also doesn't contradict with our definition of winning and losing state. There's a better way to improve our algorithm. We can separate the current state into several independent states. A state is considered independent if the empty squares are enclosed by a combination of colored squares and/or obstacles. In the example, this game can be separated into 5 independent states. 1, 2, 3, 4, and 5. An empty square is in the same state with other empty square if they are adjacent horizontally or vertically, but not diagonally. We define this condition as connected. We can separate the current state into independent states because we can only color 1 by 1 square or 2 by 2 squares which are connected. By separating the state into several independent states, we can assume this into a game of nim model with an independent state as a pile. Then we can get the number of the current state as the nim sum of the number of all independent states in the current state. The number of this independent state is 2. The number of this independent state is 1. The number of this independent state is 0. The number of this independent state is also 0. The number of this independent state is also 0. Sort of number of all independent state is 3. Therefore, the number of the current state is 3.
Because we already know that if the current state's number is 0, then the player taking that turn will lose. So the strategy to win is to make your opponent get the state with number value of 0 if there is 1. If there is none, then whatever we'll do will result in the opponent's victory.
This is an example of an AI playing optimally. By putting a 1 by 1 square here, the current state consists of 2 independent states with nim value of 1 and 1. The sort of all nim value of all the independent states is 0. Therefore, the nim value of the current state is 0. So, this is a losing state and AI will win. This is the resource for our project. We get our idea for the game from Top Coder single round match. We modified the problem to make it into our game. We also read some theorem from this paper. We also make the Little Squares game for our project. We already uploaded on this website. Please do visit it.